About a week ago, I saw a news article that was talking about a shortage of Adderall. It's a pretty common medication that's prescribed for attention deficit hyperactivity disorder. And I wanted to go ahead and talk about what is Adderall. It tells you in here it's the mixed salts of a single entity amphetamine product. These are just some pictures of Adderall bottles on a pharmacy shelf. Here's the article. It says, Adderall users struggle amid ongoing medication shortage. You know, this is a pretty easy molecule to synthesize. I'm guessing all of you could figure out how to synthesize that from a benzene ring. And why should there be some sort of a struggle with this? You know, when you see a bottle that says mixed salts of amphetamine, you should probably recognize that this is very close to the subject of Breaking Bad, that series, or what you might have heard of as speed, as a street name for a drug. All those things, amphetamine, methamphetamine, and speed refer to this molecule up here. It's the methyl N-methyl derivative of amphetamine. And what is sold as Adderall is actually without the N-methyl group. It's an even simpler molecule, amphetamine. Actually, that methyl group is not easy. A single methyl group is not easy to put on there cleanly. And what this article is talking about, it says, it talks about one pharmacist saying, I've had patients, or maybe this is the physician, I've had patients call 10, 15, 20 pharmacies in order to get their medication. So I can't quite figure out why this is so hard for suppliers, for pharmaceutical suppliers to make this in quantity. Let's go ahead and talk about the composition of Adderall. It's quite unusual, actually, and it fits exactly within one of the themes of this chapter, which is protonation of amines in order to make ammonium salts. So what they do is they take amphetamine, that amine base with an NH2 group, and they mix it. It looks kind of to me like some formulation chemist at some company, I don't know if it's Shire Pharmaceuticals, thought, oh, maybe we can get a slightly more active compound that's not patented if we make the sulfate salt by mixing amphetamine base with sulfuric acid. So that's clearly part of the mixture. But I guess that didn't have a good enough effect or a noticeably different effect from what was patented. So they then added additional acids in there, like saccharic acid. That's an oxidized form of glucose, it looks like to me. And they make another salt out of that. So now they have sulfate salts, and when it's protonated, it's not amphetamine, it's the ammonium ion of amphetamine. When they protonate it with saccharic acid, they end up with the ammonium ion. And all that's changing is this counterion, which has absolutely nothing significant to do with the biological target or the biological activity of this. And then they, just to try to differentiate this, they mixed it with another chiral acid, aspartic acid. That's the ionized form of aspartate, the neurotransmitter. That's not really the focal point of the drug. And it's a ribosomally incorporated amino acid. So they've got all these salts in there, but really the business end of this mixture is always the amphetamine, ammonium salt. That's what floats around in the bloodstream, that's what goes into your central nervous system, and that's what targets this very specific receptor. There's a high affinity receptor that is located in the neuronal signaling pathways. And so let's go ahead and take a look at the target for this amphetamine molecule. Not speed with a methyl group here, but just plain amphetamine. The target is the same. It's the same target whether you're taking methamphetamine or amphetamine. And it's this thing called the trace amine associated receptor 1, TAR1. It's a G protein coupled receptor, so if you've taken pharmacology classes or biology classes, there's about 7 major signal transduction pathways that allow small molecules to modulate transcription in the nucleus. And these molecules here target a G protein coupled receptor. So what you're seeing here is a synaptic cleft where there's transmission going between some sort of a presynaptic terminal on a nerve cell. That's over here, and it's releasing neurotransmitters to be received by this other nerve cell down below here. And there are vesicles containing neurotransmitter that fuse with the membrane and release neurotransmitter so you can transport that signal. And the reason why it took so long for people to figure out what is amphetamine targeting, it is clearly targeting something potently, it's because the G protein coupled receptor is not on the extracellular part of any membrane. The G protein coupled receptors for amphetamine and methamphetamine are located inside the cell on the vesicles. So they're kind of like, topologically, it's kind of like it's pointed to the outside of the cell, but they're actually pointed into vesicles. So they're really designed as sensors to detect how much neurotransmitter is inside those vesicles. Just like the G protein coupled receptors on the postsynaptic membrane here are designed to tell how much neurotransmitter is in the synaptic cleft. So these serve as sensors for how much neurotransmitter is packaged up inside of those vesicles. So that's Adderall. If you guys have been taking Adderall to help you study for the exams or just maintain your focus, I wish I had some to help me maintain my focus. It would probably do me some good. But maybe you've been having troubles getting it from your supplier, the pharmacist. All right, this is our last chapter in Chemistry 51C. It's the amines chapter. That's drugs like methamphetamine, heroin, alkaloid drugs, LSD. And so we left off trying to talk about how to synthesize amines using SN2 reactions. And the problem is that if you just throw in an amine to try to attack this, you'll get overalkylation. I hope I explained that pretty clearly. We do not simply throw in alkylating agents like alkyl bromides and tosylates with amines. That's not efficient. You have to use a vast excess of the amine, and we rarely have amines that we can throw away in that manner. So I showed you this trick that used to be quite common, not so much anymore, using phthalimide. This is called a Gabriel synthesis, this two-step synthetic sequence. So if you absolutely have to put a single amino group and you just can't find a bottle of excess of ammonia to dump in as excess, you could use this two-step sequence to put an amino group in place of a leaving group. Now let's go ahead and talk about some other reactions that you've already seen before for how to synthesize amine-containing compounds. So the first chapter we covered on electrophilic aromatic substitution, we taught you how to nitrate benzene rings using nitric acid and sulfuric acid. I expect all of you to know that recipe, but nobody really wants a nitro group on their molecule. If you're in the drug industry, that's toxic. It's going to cause problems. There's no drugs that I know of that have nitro groups on a benzene ring. So medicinal chemists always want to, and other synthetic organic chemists, always want to reduce these nitro groups down. And we taught you two classes of recipes for reducing nitro groups you don't want into amino groups that you do want. And without question, the easiest recipe, the one that always works in 100% yield, is hydrogenation conditions. Hydrogen and palladium on carbon. Those are the same conditions that hydrogenate alkenes, the same conditions that hydrogenate alkynes all the way. And those conditions in quantitative yield reduce nitro groups down to amino groups. And once you have this kind of an amino group here, well, now you can acylate it, you can form imines out of that, right? The sky's the limit now. You can keep making longer, bigger molecules with that amino group. Now we showed you another set of conditions for reduction of nitro groups. They're like, what if you have an alkene and you don't want the alkene somewhere else in your molecule to be hydrogenated? Well, then you'd want a set of conditions that can't hydrogenate or do anything else. And so let me show you another set of conditions. Let's suppose we had a benzene ring that had some sort of an alkene on there, and it had a nitro group on there, and we want to reduce the nitro group without hydrogenating the alkene. Now what are you going to do? I showed you another set of conditions where you use a metal as a reducing agent. Tin or iron is what the book shows, and I think I only showed you tin. Why should you have to memorize two different metals? It won't make any difference to you. So tin, I think, is a slightly more common one. Tin metal in hydrochloric acid. And the product of that reaction is not an amine, an NH2, because if you're stirring around in hydrochloric acid, that amine is going to be protonated. So the product of this reaction is the ammonium, and we have to always put the counter ion if we have a positively or negatively charged product. In this case, the counter ion would be the chloride anion, because you're stirring it in HCl. If you want the free amino group, you have to treat that with sodium hydroxide, which is pretty easy. We always work up our reactions to wash out salts and things. So it's easy to just use aqueous sodium hydroxide to remove that proton. Okay, so I don't know, let's go ahead and take a look at that two-step sequence here. Suppose you didn't want the ammonium chloride salt. Let's suppose we took some sort of a complex substrate. You could have made this, if you nitrated this using electrophilic aromatic substitution, it would put the nitro group ortho and para, but the para position's blocked, so it would go ortho, right? That's the only spot. And there's two equivalent ortho positions. I'm just showing one of those, the top ortho position. So if we wanted to reduce that nitro group down so we could acylate the amine or do something with the amine, we need a two-step sequence if we're going to use that the tin method. So step 1, tin, SN, HCl. Step 2, we have to work that up, right? Because the initial reduction is going to give us the ammonium chloride salt. Let me go ahead and draw that out, which we don't really want. We don't want the ammonium chloride salt. That's not a good looking 3. Let me fix that a little bit. And then step 2, we would add sodium hydroxide to deprotonate the NH3+. And then that would give us the amine that we wanted. I can't think of when you would actually want to just stay at the ammonium chloride salt. Maybe if you're trying to make a water-soluble drug to put into people, in theory. All right, so reduce nitro groups to amines, to aromatic amines. We call those aromatic amines anilines. That's the name for an amino group on a benzene ring is an aniline. So, and the tin method, you have to work that up using sodium hydroxide. Let's go ahead and take a look at another transformation that you've seen before that is very efficient, that is much more likely the way that you would make amide bonds, amine bonds out of amides. Now, we showed you already 2 ways. If you want to make this kind of an amine here, I don't know any chemist who would use an SN2 reaction for that. That's just not likely. When you try SN2, you've got competing E2 eliminations, all kind over alkylation, right? What any chemist I know would do is they would first make an amide in 100% yield. No competing E2 elimination, no over alkylation of the nitrogen. You just make the amide, and it's always efficient. So you should know how to make amide bonds, right, out of amines. DCC couplings to make amides, acyl chlorides to make amides. So you should know that from chapter 20, both of those transformations. That's an easy carbon-nitrogen bond to make. And we, way back in chapter 17, when we talked about all those Grignard reagents and hydride reagents, we told you how to reduce amides down to carbonyls down to CH2 groups. So you should know those conditions. I mean, at this point, you should have practiced enough problems where you should know this dead cold. So lithium aluminum hydride, step 1. And as you know, step 2 is going to be an aqueous workup. We got to get rid of all those aluminum salts and protonate any anionic groups that are in there. So that's our conditions. Well, that is just total money, this method of synthesis. This is the method that most organic chemists think about when they want to make these kinds of carbon-nitrogen bonds. So I would expect you, if I gave you a sequence that looks like this, right? If I give you some sort of an amine and I say, well, okay, tell me any steps or conditions. This is not a retrosynthetic error. I'm just asking, what are the steps and conditions to efficiently carry out this transformation to make a carbon-nitrogen bond like this? Without E2 elimination, you can't do the Gabriel synthesis. That's only for NH2 groups, to add NH2 groups through nucleophilicity. So if I ask you what for steps and conditions, I would expect you to know how to do this. So step 1 would be acylation. In theory, you could use an anhydride. I don't know anybody that would, where you would get that anhydride from, but you don't have to show how you make it. But really, the easiest thing to write, if you're just writing stuff on an exam or on a problem set, if I don't tell you, you know what reagents you have to use, I feel like DCC couplings are the easiest to envision. You take an amine, you take a carboxylic acid, and you add DCC. That's easy. And then you get an amide out of that. Boy, that's awesome. So simple. And that makes that carbon-nitrogen bond right there. Let me just highlight it. There's the new bond you just made. Carbon-nitrogen, efficient, 100% yield. No double alkylation or acylation of the nitrogen. That never happens when you make amines. You never double acylate those. under the conditions that we've shown you. That would actually be quite difficult to double acylate. Here it's impossible because there's already 3 groups on the nitrogen. And now we do our reduction step. Step 1, lithium aluminum hydride. Step 2, water. And if you make methamphetamine in your garage this weekend, you're going to be using this method to put that N-methyl group on there. It's this acyl, you make an amine, you do lithium aluminum hydride reduction. So it's not some sort of Gabriel synthesis or SN2 chemistry that you're using for that. All right, so now I want to caution you on this. It's easy to get confused about lithium aluminum hydride and reducing things down to CH2 groups. So you learned way back in that chapter 16, the chapter on electrophilic aromatic substitution, that you could reduce carbonyls to CH2 groups using 2 different types of conditions. If your substrate will tolerate brutal basic conditions, boiling and sodium hydroxide, then you can use these conditions, hydrazine, sodium hydroxide. That's called a Wolff-Kieschner reduction. You have to heat those, and that will burn down a carbonyl to a CH2 group. There was also those Clemmensen reduction conditions. You can recall those. If your substrate is tolerant to brutally acidic conditions, there were these other Clemmensen reduction conditions: zinc, mercury amalgam, zinc, parentheses, Hg. You've just got little zinc dust particles coated with a little mercury film all over them. It actually, the mercury is bonding to the metal in there. You put this in hydrochloric acid and you boil it, just like the Wolff-Kieschner conditions. And if your substrate is tolerant to both strong acid or strong base, then you can choose either one of these. It won't matter which one you use. I'm showing you simple substrates here, but in practice in the laboratory, you usually don't. You've got substituents everywhere, and you're choosing very carefully, gee, should I blast my molecule with harsh base or harsh acid? You have to choose judiciously. This looks suspiciously like these lithium aluminum hydride conditions, so I have to urge you, do not try to apply those chapter 16 conditions like Wolff-Kieschner reduction let me not even I don't even want to draw that there. Don't draw that, or put an X through that if you drew that. If you try to use these Wolff-Kieschner reduction conditions like hydrazine, what would happen if you tried to use hydrazine and sodium hydroxide and heat, and you boil that? Well, you would simply hydrolyze the amide bond, right? If that's what you did, right? Boiling things in base, you hydrolyze the amide bond, and that's not really right? If you're trying to reduce things to a carbonyl, don't use the Wolff-Kieschner conditions, don't use the Clemmensen conditions, because you're simply going to hydrolyze the carbon-nitrogen bond, which you probably just made. Again, if you want to reduce down an amide, down to an amine, then it's lithium aluminum hydride. Step 2, aqueous workup, H2O. And once you do that, now you've got another amine, right? Now you're free to take this amine group here and acylate it again, or make an enamine out of that, or do some sort of chemistry with that. So you can see that you could repeat this sequence of acylate an amine, reduce it down to make a new amine that's nucleophilic, and then acylate it again. Right? You can repeat that 2-step process of lithium aluminum hydride and water. Now, you learned lithium aluminum hydride, applying that to another functional group. We had this chapter, chapter 19, that was all about carboxylic acids. Carbon atoms bonded to with 3 bonds to heteroatoms, C double bond O with another oxygen. That's a carboxylic acid. And they slipped into that chapter, at the end of the chapter, a bunch of interesting chemistry involving nitrile groups, a carbon bond with 3 bonds to heteroatoms, except nitrogen in that case. And you can add to C triple bond N to nitrile groups, to cyano groups, also called, in the same way that you can add to carbonyl groups. So we taught you in that chapter that you could use these same lithium aluminum hydride conditions. Step 1, lithium aluminum hydride. Step 2, H2O workup. And that will convert this C triple bond N into a CH2 a methyl amino group. So notice that this method will always produce a CH2NH2 group. So whenever I see a CH2NH2 group in my product, I'm thinking, oh, I could have made that through reduction of a nitrile. You have to practice enough problems to recognize that when you have a CH2 group, NH2 group in your product, that you ought to be able to make that through reduction of a nitrile. So if I ask you to make something like this down below, you should be thinking, well, I got a lot of ways to make that, but clearly you have to add another carbon atom. Your starting material has one benzylic carbon, but your product has two CH2 groups. This is a perfect situation for using this nitrile reduction thing. So how would you do this? Well, it's pretty easy to displace benzylic groups. Look how great this substrate is, right? There's no beta hydrogens. You can't possibly do an elimination to make an alkene here. The only thing that can do is SN2. So here we're well situated to do a simple SN2 reaction that has no possible side reactions. That's sodium cyanide or cyanide anion. Could you use potassium cyanide? Yes. Sodium cyanide's the common and expensive one. And so that will make a new carbon-carbon bond. The cyanide anion will act as a nucleophile and then displace that. I'll draw the carbon atom here. So now we've got two carbon atoms hanging off of this benzene ring. And now we reduce this using our lithium aluminum hydride procedure. Step 1, lithium aluminum hydride. Step 2, water. There we go. We've never used lithium aluminum hydride without having a second water step. You can't write lithium aluminum hydride, comma, water. That's completely wrong. I would count it wrong and give you no points. It's step 1, lithium aluminum hydride. Step 2, water workup. Okay, so be on the lookout for that CH2NH2 thing because that you can get through reduction of a nitrile. All right, let's go ahead and take a look at a reaction you have not seen before, and it's a powerful one. Maybe the most important new transformation you'll see in this chapter in terms of general use, much more widely used in the pharmaceutical synthesis and the pharmaceutical industry to make complex molecules. And we refer to this process, this reaction transformation, as reductive amination. So we're going to reduce a carbonyl group from a double bond to a single bond, and at the same time change it into carbon nitrogen. And so here's the general theme. Whenever you want to make a bond like this right here, right, you could have made that from a carbonyl in one step just by mixing the right things together. So that's really an absolutely essential disconnection for you to be able to see if you're working backwards or forwards doing synthesis problems. So let's go ahead and take a look at the secret reagent. You can see what we're doing is if we want to make this bond right here, and you can see there has to be an H there. That's kind of like our staple to hold them together. You can make that from a carbonyl and an amine group. And so what's our secret condition? It is a reagent called sodium cycanoborohydride. Let me go ahead and write this out. I hate the way they write this with a molecular formula. So it looks like this, CnBH3. I'm pretty sure that's the way the book writes it. And the reason why that bugs the heck out of me is because it makes you think there's a nitrogen-boron bond. Let me go ahead and draw out the chemical structure of sodium cycanoborohydride. So it's kind of like sodium borohydride. Sodium borohydride has 4 hydrido groups on there, but somebody figured out that if you put a cyano group on there, that becomes a very choosy hydridoborate reagent. So choosy. It's really unreactive. It doesn't react with carbonyls. It will not reduce C double bond O. And that's pretty important because you want to throw in a hydrido. You don't want to, in this transformation, you don't want to reduce this alcohol, this carbonyl down to an alcohol, right? So you don't want to use sodium borohydride. That would simply reduce this instantly. Right? In a minute, you'd have reduced all your carbonyl down to an alcohol. But that's not what happens here. Sodium cycanoborohydride is very choosy. It only reduces iminium cations. Let me go ahead and draw out another example of using this transformation. Let's suppose that I wanted to make a molecule that looks like this. I'm not drawing out the benzene ring here. I'm not drawing out the phenyl group. Let's suppose that I wanted to make that somehow. Well, to me, that's just screaming oh, reductive amination. And this is a great way to add secondary amines. Yes, you could make this through reduction of an amide, right? I hope you can see that I could have reduced an amide here, but there's also another way I could have made this from dimethylamine, right? And that's this reductive amination process. So instead of acylating the amine, and then you doing a lithium aluminum hydride reduction, I could simply mix that with an aldehyde and use sodium cycanoborohydride. Look how easy that is. And the reason I know that will work is there is at least one hydrogen next to that nitrogen. That's how I know I could have made that. In this case, there were two H's on the carbon next to the nitrogen, but you need at least one. You know, the presence of one hydrogen on there tells me I could have made that bond. And if you're looking closely, you'll notice you could have made the bond on the other side as well, because there's CHs on the other side. Like when you make an amine with 3 alkyl groups on the amine, you usually have your choice of which carbon-nitrogen bond you're going to form last in the synthesis of that. So how does this reaction work? I told you sodium cycanoborohydride does not reduce carbonyls. It's so choosy. The reason why this works is when you mix an amine with a carbonyl, there's a tiny equilibrium amount of an aminium ion floating around. I'm not going to draw out all 5 steps. I expect you to know the five mechanistic arrow pushing steps for formation of aminium ions whenever you have aldehydes. There's a tiny amount of aminium ion in here, and you might be saying, well, Dave, you told us that you have to have acetic acid for making amines, aminium ions, and enamines, and you're right. In fact, the recipe is sodium cycanoborohydride with acetic acid, and the book doesn't tell you that, so I'm not going to make you memorize the fact that there's acetic acid in this recipe. Yes, there's acetic acid in here. Okay, so this is the whole point of using sodium cycanoborohydride. Is sodium cycanoborohydride with that electronegative cyano group on there doesn't reduce the carbonyl, but it will reduce these super reactive aminium ions. Aminium ions are way more reactive than carbonyl groups. That was the origin of the field of organocatalysis that won the Nobel Prize. I think the year before last, it was just recognizing that aminium ions are way more reactive than carbonyls, and it's easy to have equilibrium amounts of aminium ions. So you can't isolate aminium ions. We don't tell you how to do that. So if you put in sodium cycanoborohydride, you get reductive amination. So on these reactions, I didn't show you one here, but you have to watch out for the creation of stereogenic centers. So up above here, if I had 2 different alkyl groups on that ketone, then I would have created a new stereogenic center in that process, right? If this had a different R group here, let me go ahead and draw it here. If R is not methyl, then I would have created a new stereogenic center, and I would have had to use dash or wedge and write +E to clearly indicate that I generated 2 enantiomers in the product, or 2 different configurations at that carbon atom. Okay, so you've never seen this reaction before, and you've got, what, like a week and a half to learn this, and all the other reactions you've had basically 9 months to learn it, so all I can say is this is a super important reaction. You have to learn this, how to use this every which way for any organic chemistry course that covers amines. All right, this seems weird to me. Let's take a little break. What have we done so far in this chapter? I've reviewed some spectroscopy, not useful for nitrogen really, except for that IR trick that I showed you. And I talked about transformations, synthetic transformations to make amines, to make carbon-nitrogen bonds mostly, when you're synthesizing amines. SN2, not that useful. Reduction of amides, awesome. Reductive amination, you need to learn that, powerfully learn that. And then midway through the chapter, it says, okay, let's stop and talk about the reactivity of amines. So I'm going to take you back to the first thing we talked about, which is the 2 reactive roles that amines can play. Amines can be bases in acid-base reactions, and amines can be nucleophiles for forming bonds to carbon. So let's go ahead and separate those 2 And we'll talk about just the intrinsic reactivity of nitrogen versus other heteroatoms, or versus other atoms in the second row. So recall that I'm going to use the word base, right? If I take the same amino group, triethylamine or ethylamine or benzylamine, depending on what mechanistic role it has in my reaction, I might refer to that as a base. That means I'm talking about proton transfer events. Those are fast, they are reversible, very fast. You almost never can stop these from happening. There's always this very fast and reversible backwards and forwards proton transfer process. And so we're going to have to talk about this. I expect you to be able to estimate the equilibrium constant whenever you have an amine floating around with potential acids, right? You need to know whether the reaction favors the protonated ammonium ion, which has no lone pairs on it and can't act as a nucleophile, versus the amine starting material. And that's important. One of these is water soluble, the other is membrane soluble and can cross membranes. So one of these is good for formulation as a drug that you take as a pill because it's soluble in water. The other, not really. Probably just give you a stomach ache. Okay, so, and you also need to know about amine lone pairs acting as nucleophiles, making carbon-nitrogen bonds. Maybe not so much SN2, but attacking carbonyls to make aminium ions and amides. So when I use the word nucleophile, I'm talking about attacking carbon. And you can make bonds between phosphoryl groups and nitrogen or sulfur and nitrogen. That's not really the subject of this chapter so much. Now, let's just talk about the relative reactivity of nitrogen versus other elements in the periodic table, in the second row of the periodic table. So if I look at the elements in the second row of the periodic table, carbon, nitrogen, oxygen, fluorine, marching across the second row of the periodic table, things are becoming more electronegative. Right? I'm not real good with memorizing numbers and stuff. I know that the electronegativity of carbon is 2.5. That's kind of all I know. I'm not real smart. I can't add two numbers together. And because I know that number, I can predict the electronegativity of nitrogen. It's 3.0. And I'm not real smart, but I know the electronegativity of oxygen is 3.5. Can you guess what the electronegativity of fluorine is? I'll bet you couldn't guess in a million years. Yeah, it's 4.0. Yeah, that's right. And it's the most electronegative element in the periodic table. All of, the nitrogen, the oxygen, and the fluorine have lone pairs. And so we can talk about the nucleophilicity of an amine, of an ether, of an alkyl fluoride. And it has to do with how electronegative these atoms are. The most electronegative atom does not want to give up that lone pair. Fluorine, alkyl fluorides are not nucleophilic. The fluorine atom on a fluoroalkane is not nucleophilic. This is one of the reasons why medicinal chemists love to put fluorine on their drug molecules for you to take, is because those fluorines have no nucleophilicity for doing stuff. So the electronegativity in this case, the least electronegative, the least nucleophilic, is the most electronegative atom. Fluorine is the least nucleophilic, fluorine lone pairs. And as long as I'm just talking about neutral molecules, oxygen is the second least nucleophilic, and that means of these things that have lone pairs, amines should be the most nucleophilic of these. Most nucleophilic, amines. Substantially more nucleophilic than oxygen. How much more nucleophilic than oxygen? About 10 to the 12th. Right? About 10 to the 12th more, just going based on basicity values, it's about 10 to the 12th more nucleophilic when you're a nitrogen atom. What is that? Like trillion times more nucleophilic? That's what makes this a separate chapter, is nitrogen is vastly, vastly, vastly more basic and more nucleophilic than oxygen. Now, we can do the same comparison if we talk about the anionic forms of these. We can't mix these two groups together, but if I compare the anionic forms, even carbon can be a nucleophile if you're talking about carbanions or carbon lithium, carbon sodium. Those bonds are kind of like carbanions. If I compare a carbanion with an amide anion like LDA or sodium amide, with an alkoxide like potassium T-butoxide, or with a fluoride, we haven't talked about fluoride as a nucleophile. It's not a good one. You're almost always going to get competing E2 elimination if you try to use fluoride for SN2 reactions. So I don't think we've ever in this course talked about using fluoride as a nucleophile. It's really inconvenient. And hydrofluoric acid, unfortunately, dissolves bone, so we tend not to like that very much in the lab. So in this case, that electronegativity idea still holds, right? I know the electronegativity of carbon is 2.5. That's the electronegativity. And as we march across the second row of the periodic table, all the atoms are the same size, and the only thing that's changing is the electronegativity here for us to think about. Fluoride anion is the least nucleophilic of this group, least nucleophilic. And the most nucleophilic of this group is now carbon. There was no lone pair in the previous series, but now we've got the lone pair on carbon. That's the most nucleophilic. Wow. Boy, most nucleophilic. And this is all electronegativity. I expect you to be able to take a look at a periodic, I expect you to memorize the second row of the periodic table. And you don't even have to memorize that much, just these 4 atoms. Right? Nobody's going to put, we haven't been really talking about boron lone pairs in this course. That's not a standard part of organic chemistry. But I expect you to know that carbanions are more nucleophilic than amide anions, and that amide anions are vastly, 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 vastly more basic than alkoxide anions. That's why we use LDA. It's so superior. Okay, so you need to know that amines deserve their own chapter because they are so much more nucleophilic than other neutral things. And the same rules apply when you talk about anionic forms. So that's just electronegativity. And it's one of the first things you should have covered in any organic chemistry course. All right, so let's go ahead and talk. One of the things that makes nitrogen so confusing is that it exists in so many ionization states where you add groups or remove groups in order to create charges. And so I want to talk about 3 completely different species, utterly different species. I want to talk about amide anions. You notice how I say amide? I'm trying not to confuse it with amide, like a peptide amide or a carbonyl amide. So I purposely pronounce it differently, even though you're not supposed to pronounce it differently. Well, it's not, there's no rule about it. Okay, amide anions are negatively charged, and probably the most important example of amide anions is LDA, lithium diisopropyl amide. Now you can draw that with a covalent nitrogen-lithium bond, or you can draw it lithium plus and N minus, but that just has crazy basicity. And in this case, they really hinder the heck out of that with those 2 isopropyl groups. So it just kind of gets really choosy and plucks off the right proton from the least hindered side. So that's the negatively charged version, amide anions. Insane, insane, insane. Those are super basic. Let me just write that here. Super basic. Super duper basic. Insane basicity. So 100% yields in deprotonation with no leftover ketones or carbonyl alpha protons. Now, there's another form of amines that we'll talk about, that we've been talking about, just amines. When I use the word amine, I'm talking about something that's neutral. Triethylamine, ethylamine, methylamine, octylamine, putrescine, heroine, mescaline, all the drugs, methamphetamine, all the drugs that we talk about, we use names that refer to neutral forms, even though the pills you take are usually not the neutral forms. I'm drawing triethylamine here. Triethylamine, this is the lone pair that matters. That's our go-to base in an organic chemistry laboratory because it's soluble in organic solvents. Sodium hydroxide is not soluble in organic solvents. And when we use triethylamine, we're just using it to act as a base, not as a nucleophile for any kind of a reaction at carbon. Triethylamine is solely intended to serve as a base, nowhere near as nucleophilic as an amide anion. I'll write slightly basic, and that's what we want when we use that in organic chemistry as a base to throw in with our reactions. Like if you're acylating an amine and you want to soak up the HCl, you use triethylamine. Now there's another form of amines where we add a proton, and in this case, there's no lone pairs on here. There's absolutely no way that ammonium group can act as a base. And so I'm going to make it totally clear that this is not at all in any way basic. It's not a base. It's not. And this is the form of amines when they're floating around in your in your bloodstream, in the human serum, in the blood, inside of cells, in the intracellular milieu, in the cytosol. This is what a side chain of a lysine group looks like. There's no lone pairs. It's not nucleophilic. It exists as an ammonium ion. 99 to 99.9 out of every 100 lysine side chains looks like this. It can't attack anything, but it does confer solubility in water to proteins when you've got the surface of the protein covered with these positive charges. Now, I expect you, if you take an amine and you take some sort of an acid or any form, any one of these forms, and treat it with anything that's basic or can potentially act as a base, I expect you to be able to predict the equilibrium constant for that process, because proton transfer events are fast and reversible. So let me go ahead and draw out a process where we think about an acid-base event between hydroxide and an amine. I'm not saying this is good, but it's just kind of hypothetical. And so what would happen if we did an acid-base reaction using hydroxide anion to deprotonate an amine? Is that reasonable? I mean, how do we think about whether this is a reasonable process or not? Here's how we would do that. First, I would transfer the proton. Whoops, whoa, I got too much stuff written on there. Way too much stuff. Based on my reaction, I'm using the hydroxide to pull a proton. Let me just be clear here. I'm using the hydroxide to pull off that proton from the amine, and that would give me an amide. Boy, this is crazy. Why would I even draw this? I guess we're drawing it just to talk about it here. So the way you think about the equilibrium here, the thermodynamic favorability of this, the back and forth on this, is what we want to do is we want to think about the acid on each side. And why would we want to do that? Because the book has tables of pKa's, which mean acidity. The book does not have tables of nucleophilicity. The book does not have tables of basicity. The book has tables of acidity, pKa's. Why is that? Because titrations are easy. You've done titrations. Everybody's done a titration. It's dead easy. So we make tables and tables of pKa's. So you have to back out nucleophilicity using pKa values. So let's go ahead and talk about the acids on each side of this equation. So over here on the left, we've got an amine, and that has a pKa of somewhere between 35 and 40. I think I looked this up and it was 40. So it doesn't matter whether you use 35 here, which is, I think, the number we gave you for most amines, or 40. You'll draw the same conclusion about whether the reaction should go forward or backward. But if you use 35 here, no problem. Again, amines, the pKa's vary depending on the substituents. So if we look up the pKa for water, well, you shouldn't have to look that up. You should know the pKa for water. Alcohols, water, 16. That has nothing to do with pH. That's a different concept. Water's pKa 16. Ethanol, pKa 16. Methanol, close enough to 16 that you should just memorize 16. Okay, so because we have pKa tables, we can know the pK values for the two acids. If you had a table of basicities, you could assign some number to the bases in these equations, but you don't have that. You have pK tables. And you can use these two pKa's to estimate the equilibrium constant. And I've shown you the secret equation here that looks scary. It's, my gosh, how am I going to memorize that? It tells me that I can predict the equilibrium constant for this rapid equilibration process simply by using this equation. So let me show you how easy this equation to use is, even though it looks scary. The way we use this equation is 10 to the difference of pKa's. So pK of the products minus the pK of the reactants. Now I can do that. I mean, if I can do that with my limited math ability and you've just taken Math 5 or whatever calculus course, you've got to be able to do this kind of math. So here's the way we do it. We say KEQ, equilibrium constant, is equal to 10 to the 16 minus 40, products minus reactants, which is equal to 10 to the negative 24. So if I tell you that the equilibrium constant is 10 to the minus 24, which side is favored in this equilibrium, products or reactants? The reactants are favored by 10 to the 24 value. Right? At equilibrium, what this tells us is the equilibrium ratios of product side versus the reactant side is 10 to the 24. Okay, I ran out of room there, but you get the idea. All I needed to do is look at a pK table, and it's very clear which side of this equilibrium is favorable. Right, a mole is 10 to the 23rd, so if you had a mole of these reactants sitting in there, you wouldn't even have one molecule that's deprotonated at equilibrium. This is not a reasonable reaction for you or anybody else to draw. No alkoxide is ever going to deprotonate a simple amine. You can predict that by knowing some simple pKs that we've already given you, and you just have to master this challenging secret equation here, Ke, or you could derive it yourself using some simple algebra. But it's easier just to memorize that. So I expect you to be able to use this equation to predict when you dump acids and bases together. I expect you to be able to predict whether that's favorable in the forward or the backward direction. You should be able to figure that out. Now, this is not for buffered conditions. This is not the equation you use to figure out whether things are going to be protonated or deprotonated inside of a cell. They're not things that you would use to figure out whether things are protonated or deprotonated when you take a pill. Those things all occur under buffered conditions. Your blood is buffered by bicarbonate and other groups. The inside of cells is buffered, and there you use the Henderson-Hasselbalch equation when you're doing chemical biology or biochemistry. If you want to figure out the ratio of protonated, HA, to deprotonated at any pH, you just need to know what the pH is buffered at. So in your biology classes, everything's buffered, and so you figure out the ratios of protonated to deprotonated using Henderson-Hasselbalch equation. I can't even remember, whether, I can't remember the Henderson-Hasselbalch equation. It's like, gee, is it pH minus log or whatever? I can figure it out intuitively, but I don't ever remember the math equation for that. This is much simpler, so. Okay, so I'm going to go ahead and stop right there. When we come back, I want to talk about this concept of freebasing. Like if you go off this for Thanksgiving and you're freebasing Coke, you want to understand what that concept means. We use the same concept in the lab when we want to isolate neutral amine compounds. So you guys have, oh wait, we still got another lecture on Wednesday. So come back on Wednesday. Thank you so much for coming here early in the morning. I'll see you guys in a couple of days.